So, greetings everyone. Myself Ateeb Nasir. I'm a PhD student at Department of Electrical Engineering, IIT Kanpur, and I will be solving the uh, numerical assignments during the coursework. So, this course is taught by Professor Sanjeev Sambadan, and I will be TAing the course. I request yourself to keep yourself muted during the whole discussion, and if you have any question, you can put it in the chat window. So, am I clear? Any response?
Okay.
Okay, it's fine. So, I think we should begin because it's already 5 and just 4 or 5 people have joined, 6 people to be precise. So let's start. So, uh, let me begin with solving some numerical questions in the course. As you had already seen in the course taught by the professor, he started with the quantum mechanics and the wave functions. So let us see that if we can solve this question one, which I have put in here, so that you get some knowledge about these physically realizable states in the quantum mechanics. So basically, what the question says, it says that if we have two physically realizable states, that's psi 1 and psi 2, so if we have any linear combination of these two states, whether it will be physically realizable or not. So I request everyone to join by 5 uh, from next meeting onwards, because it will be convenient for me as well, so that I do not have to interrupt while solving the assignment questions. Since it's first day, I am admitting all the students, even if they join up to 5 5. So let us start. As I already said, that we have to see whether this linear combination of these two physically realizable states will be physically realizable or not. So let us see what we mean simply in here. If we have this psi 1, we know that if these are psi 1 and psi 2 are physically realizable, then it has to be somewhere in the space. So let me simply write it where this a squared, where this a is the normalization constant, and this psi 1 of x comma t is the wave function, and this is the first realizable state that I was talking about. If we look it into the space, it has some finite probability that it will be there. So it will not be infinite, it will be some quantity which will be less than infinity, as we had already seen taught by the professor, that this is the condition for the wave functions. Similarly, if we have the second state psi 2, and psi 2 will be having the same property, that is minus infinity to infinity, it should exist somewhere in the space. So it has less than infinity. Now, as we know, what we have to do, we have to just evaluate the psi star psi. And as I have already said, that we have to look into the linear combination. So linear combination of psi into psi star, which will just look like minus infinity to infinity a times psi of first physically realizable state plus b times psi 2 of x comma t, its conjugate, multiplied by the a times psi1 of x comma t plus b times psi2 second physically realizable state psi2 of xt dx. Now we just have to take the conjugate and do the multiplication, the required steps. It will look like minus infinity to infinity if I take the conjugate, and I will assume the constants are here, the real constants. So a times psi1 star x comma t x comma t plus b times psi2 x comma t, it will be also conjugate, and this will be multiplied by psi of a times psi of first realizable state plus b times psi2 of x comma t, and the integral is over the x direction. Since we are considering 1D only, 1D case only. Now, if we take its conjugate and multiply the terms by itself, it will look like minus infinity to infinity. It will be a squared psi1 of x comma t whole square dx plus minus infinity to infinity ab. Yes. So Mitra, I will be sending this PPT. You don't have to worry about that. And wait a second, there are many students who are trying to get in. So this, what I was saying, I will be preparing this PPT and I will be uploading it. So no worries about that. So this AB, I have said these are physical. These are the just the constants. So if I now see this, I will multiply this psi1 star x comma t with the psi2. This is the other physically realizable state xt, and integrated over dx. This is just the multiplication what I am doing in here, and this will be minus infinity to infinity ba. These are the constants psi2 star x comma t and psi1 x comma t dx plus minus infinity to infinity b squared psi2 of x comma t integrated over dx. So here we see we will be having four terms, and as we have seen earlier, this term we will be knowing, and this term also we know this, we know these quantities are already known to be less than infinity. Basically, for the wave functions to exist, they have to live in Hilbert space. So let's not go into the more details of that. You just remember that they have to be uh, less than the infinity. So now we use some identity that's known as, let me write it, by Cauchy Schwarz identity. It says that if we have of psi1 and psi2 which are square integrable, then their inner product must exist. So let me write it down like this. If 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 i request everyone I request everyone to join by time from next time onwards. Please join on time. So if these psi1 and psi2 are square integrable, what we will be having, it says that their inner product is guaranteed to exist. And it says that this integral between the limits a to b psi1 of x comma t psi2 psi2, let's drop the time, let's keep it in the space only. Psi2 of x dx should be less or equal to limits a to b psi1 of x dx a to b limits psi2 of x squared dx, whole term under the square root. So what does this show? Since this quantity has to be always less than the their square root term, and we know how these terms are related. These terms, let me put it in the magnitude, so, because we know that this integral minus infinity to infinity a squared psi1 of x comma t square dx is less than infinity. Now it means that this second term over here, this second term and this third term, we can use this Cauchy's formula, and we can say that this is also less than infinity. So similarly, the other part of the integral, which is this psi2 star into psi1, psi2 star into psi1, this is also less than infinity. So what we have seen, that by simply using this relation, we have shown that this the terms in this expansion of this linear combination uh, are also less than infinity. So this linear combination combination of psi1 and psi2 is also physically realizable. So what we have seen, that if we have two wave functions psi1 and psi2, and if we have their linear combinations, and if these psi1 and psi2 they are physically realizable, then their linear combination will also be physically realizable. So if we see now, the second question that I have put in here is that it is related to the uh, operators that professor taught in the class. He told that we will be having the position operator, the energy operator, and the momentum operator, operators like those. And in here, what this question 2 says, we just say that if we have some wave function whose position is denoted by this x, and we know that this position vector, since it's observable, we can write it in terms of the integrals, and it will be simply minus infinity to infinity psi star, and this is where we put this operator, this position operator x, psi of x comma t dx. This is simply the position operator. So what we are here told to do is that we need to get the velocity and show that this velocity is given by this relation, this relation. So we are going to proceed by just derivating this dx by dt. As we know, this velocity is the time derivative of the position. This is just from the basics. So if we do this, we will be just writing d by dt of minus infinity to infinity, the limits of the integral psi star x comma t x psi of x comma t dx. So since I can take the d by dt inside, I can write it to be minus infinity to infinity x times d by dt of psi star x comma t psi of x comma t, and this will be integrated over x. So simply we will be using here the product rule, and it will be minus infinity to infinity x times, if we use the product rule here, it will simply be psi of x comma t d by dt of psi star x comma t plus, let me put this in bracket, plus psi star of x comma t d psi of x comma t by dt, and this will be integrated over the x space. So what we have seen, that we have just used the product rule in here, and we also know that if we use the Schrodinger equation, the time dependent one, we can write it to be like this. Using Schrodinger's equation, we can write it to be iota h bar d psi by dt is equal to minus h square by 2m d square psi or dx square plus v psi, where this v is the potential and this psi is the wave function. Or if we divide by iota h bar, we will get d psi by dt to be equal to minus h bar iota by minus h bar minus h bar iota by 2m d square psi by dx square plus v psi. So now if we take the conjugate of this, we will be simply getting, since I have missed some here, yes, I have missed here this minus iota by h bar, since I am dividing by iota h bar. So I am getting this relation. So now if I take the conjugate of, let me name this equation 1, I will be getting d psi star dt equal to, mm, since I have taken conjugate, this will be plus, this will be minus h bar iota to m d square psi star dx square plus iota v psi h bar. Let us check the correctness of this. Well, it's absolutely correct since I am doing this. Okay, since I have taken the conjugate, I will be writing d psi star minus h bar iota d square psi plus iota v. So it's absolutely correct. So if we now see what we have in here, we have somewhat terms like that. That is d by dt of psi star and d by dt of psi. So if we try to use these relations, this first and second that we obtained, and try to see what this the quantity psi d psi star dt plus and psi star d psi dt will look like. It will simply be minus h bar iota by 2m d square psi by dx square plus plus iota h bar v psi into psi star plus the term over here should be psi. Yes, since we are multiplying by psi, it should be minus h bar iota psi, and this is absolutely correct. This is iota v psi into psi star, iota v psi into psi star by h bar, and this first term should be, since I am multiplying by psi star, it should be h times h bar times iota divided by 2m. It should be psi star d square psi by dx square minus iota h bar v psi into psi star. Clearly, we can see that this term and this term will go, and we will be left with minus. If we take this minus and minus should be on the right, and if we take this h bar iota 2m to be the common factor, we will be getting psi star d square psi by dx square minus psi d square psi star dx square. So let's name this equation as equation 3. Now let us do some manipulation with this equation itself. We know that if we write it to be like this, d by dx of psi star d by dx of psi minus psi of d psi star by dx, what we get? What will we get? So the if we use now the mm, uh, product rule itself, we will be getting d psi star dx, and it will be d psi by dx, and it will be plus psi star d square psi by dx square, and this term, the second term, will simply be minus of d psi by dx, and it will be d star psi star by dx, and it will be minus d square psi star d square psi star by dx square. So what have we got? We have just tried to use this equation and try to manipulate it by just using this dou by dou x. And what we observe from this is that if we see this term and this term, these both terms will cancel out. This term and this term both will cancel out, and we will be getting this integral, this expression simply to be equal to d psi d by dx of psi star dou psi by dou x minus psi dou star by dou x will simply be now equal to psi star d square psi dx square minus psi d square psi by dx square. So this is simply the equation that we are going to put to be equal to equation 4. Now we will use this equation, sorry, we will use this equation 3 and equation 4, and we can write the dx by dt to be simply equal to h bar iota by 2m. And what we will be doing, we will be simply replacing the quantities over here, we will be replacing them, and we will be just getting the simplified integral, which will be minus infinity to infinity, since we have x dou by dou x psi star, this is the term in here, d d square psi d square psi by dx square minus psi d psi star by dx. So this is what we will be getting in here. Now what we have to do, we have to evaluate this expression as well by just simply using the uh, integration by parts. So what we will do, we will use the integration by parts and we will just integrate it. We will write it like this using integration by parts, integration by parts, so that it's clearly clear to everyone. We can write it to be h bar iota by 2m, h bar iota by 2m. So wait a second, let us see. Okay, this we have deduced. This should be d psi and this should be d psi. Since we have replaced this quantity over here, this should be simply psi star. Uh, since I have written it to be d by dx of psi star d psi dx minus psi by d psi by dx, I have to write this one. I have replaced this one over there. So simply, if I now do the integration by parts of this, it will be simply the 2m minus infinity to infinity. So I will just use this x as it is, and I will go for the this second part. This simply will be psi star. Since I am integrating with the x dx, it will simply mean that I will be getting psi star d psi by dx, since I am integrating over x. Since I am integrating over x. So this simply will means d psi star d psi minus psi d psi star by dx, and these will be having the limits. We have to integrate it between the limits from minus infinity to plus infinity. But we know, we know that uh, the psi for it to be physically realizable, that it has to tend to 0 if x tends to infinity. So this term over here, it should vanish completely. This term should vanish over here. It should be 0, because we know that for the system to be physically realizable, this condition has to be true. So if we see the other part of this term, it will be just by simply using the integration by the parts, it will simply be minus h bar iota by 2m minus h bar iota by 2m. Since I am using the I have to derivate the x, I will be getting minus infinity to infinity psi star psi star psi star d d psi by dx minus d psi star by dx of psi, and this will be integrated over the whole space. So what we have done, we have reduced this expression for the velocity to be equal to minus h bar iota by 2m minus infinity to infinity psi conjugate d psi by dx minus psi d psi conjugate by dx with its integral over the space of x. Now let me do another manipulation and keep this as it is and go towards the second term of this expression, and we will simply see that we will be getting minus iota h bar by 2m. Let us keep it as it is, psi star d psi by dx integrated over dx, and integrate this second part in by using the integration by parts. So what we will be getting, we will be simply getting minus psi into psi conjugate with the limits between minus infinity to infinity, and the second term will simply be minus infinity to infinity psi conjugate d psi by dx integrated over dx. As we know that this term must be 0 for the system to be physically realizable, and that was the condition that we had taken previously in the beginning. So it simply means that we just we just have to we just have to handle the first two expressions, and these two expressions simply will add up because we can see that the limits of integration are same, and also the integrand inside is also same. It's just the psi star d psi by dx. So we can write it to be dx by dt to be equal to minus h bar iota by 2m minus infinity to infinity. Since these two will add up, this will be psi star d psi by dx integrated over dx, and this 2 and 2 will go. What we will be getting, we will be simply getting dx by dt to be equal to minus h bar iota by m minus infinity to infinity psi star d psi by dx. So this is what we are left with, and let us check whether we wanted this. Yes, this is the result we wanted, and we have obtained this velocity just by going through the steps by using that this velocity will be the time derivative of the position, and we have gone up to this position and seen that it will simply give us the it will simply given by this expression which we have derived just now. This will be the velocity if we have some position. So if we now move towards the another question. So it what does it imply in here? It shows that it the question says that if we have infinite potential, example as taught by the professor in the lectures, that if we have the solutions to that infinite potential, we have to show that these solutions are orthonormal. So let me first write the uh, wave function itself. What how does it look like for this infinite potential well? We know that the wave function wave function. One second, let me check the chat. Okay. Any questions till this? You can put them in the chat if you have any question. So we know that okay, it's fine. Thank you. What do you mean by numericals? Can you please elaborate in chat? Till that, I will just write down the uh, solutions of this in this infinite potential well. We know that the nth solution will simply given by 2 by L. This has been derived by the professor in the lectures. Sine of n pi by L x, where this L was the length along the x, and this 2 by L was the normalization constant that the professor obtained by using the condition on the psi that it has to be between the minus infinity to plus infinity, and the professor had obtained it to be equal to root by 2l. And that's now we are going to look if we have two solutions, whether they will be orthonormal or not. So simply, if this is the nth solution and it is denoted by this psi n, now let me write down the mth solution. Mth solution, it will simply be given by root by 2l sine of m pi by l x. Here, let me clarify, these n and m are the integers, and these have been shown by the professor itself in the lecture that these are the integers, and for a ground state the value of n should be 1, and correspondingly we will increase its value, and he also showed you how we will be able to obtain the energy corresponding to these as well. Questions related to the lectures taught by the professor, more on numerical questions with data. Pasai, I am not getting you. Maybe at the end, I will allow you to speak. We will try to wrap 5 minutes before so that I can listen to your query and I will address to that. So this what I was saying that if we have now two solutions to this infinite potential problem, that we will write it with the psi n and psi m, and these simply what we have to show that this inner product, we have to check this inner product which will be having the limits between actually 0 to infinity, but since we know that it is infinite, this the potential barrier is infinite and the particle will be lying between 0 to L, so we will simply integrate it over 0 to L psi m star x, and this will be psi n x dx. This is the inner product. So if I use this psi m and psi n, and if I conjugate this psi m, I simply will get the sine pi by L x itself, and it will be simply root of 2 by L sine of m pi by L x, and this psi of n will simply be 2 by L sine of n pi by n pi x by L, and this will be integrated over the x space. So what we have done, we have just used it, and let me, for the convenience, write it to be equal to I. I is the integral. Integral is equal to this thing. So simply, if I take these constants out, I will write I to be equal to 2 by L with the limits 0 to L sine of m pi by L x sine of n pi by L x, and this will be integrated over x. So simply we will use some uh, trigonometric identity, and you all must be aware that if we have sine of A, sine of B, it will simply be written in terms of cos A minus B minus of cos A plus B divided by 2. This is the simple relation between the two. So what we have seen here, we will be using this identity, and in our case, this A will be m pi by L, and this B will be n pi by L. So we have simply we have to simply use this relation to evaluate this integral. This will be 2 by L integrated over 0 to L, and let me put it, this cos term, cos will be simply m pi by L minus of n pi by L, and it will be having x here, and we will be having cos of A plus B, which will be m pi by L plus n pi by L x dx. So this dx is for the whole. So what we have to solve this integral, and I think I missed the factor of 2. Yes, it should be divided by 2 as the identity says the same. So I will be getting I to be equal to you can mute yourself, Utkarsh. I to be equal to 1 by L 0 to L 0 to L m pi by L. Let me uh, take this m pi by L as common. We will be simply writing it to be cos of m minus n pi by L x, and the second part will simply be, let me take the m pi by L common there as well, cos of m plus n pi by L x, and this has to be integrated over dx. So we have got rid of the two factor as well, and now we have seen that this expression reduced in terms of cos only. Now we can simply evaluate this integral, and we know that cos can be written like this. Since this is cos, we know that it will be sine of m minus n pi by L x, and this will come in the denominator pi times m minus L. Simple. It's that simple. And this will be having this will be having this will be having the limits between 0 to So similarly, we will be having the second term as well, which will be minus 1 by L, and it will be simply L by pi m plus n, and this will be having also the sine of m plus n pi by L of x with the limits 0 to L. And we know that sine of 0 is equivalent to 0, and we can put these limits in our equations, and we will simply get it to be equal to 1 by pi. I will be cancelling this L and L. This will be m minus n. This will be sine of m minus n, and since I am putting x equal to L, L and L will go. This will be m minus n pi, and similarly this over here L and L will go, and this I will be left with pi times m plus n, and I know that sine of 0 is equal to 0, so I will be left with sine of m plus n, and pi by L, since I'm putting the limit to be x, limit x to be L, it will simply L and L will cancel, it will be sine of n pi. So this is simple what we have got in here, and we know that these m and n are integers. So uh, if uh, if we have any number for which m is not equal to n, this integral over here, this I integral will simply be equal to 0, because if we see that n has some value, let's say 4, and n has some value that is 2, and we know that m minus n, 4 minus 2 will give us 2 pi, and similarly m plus n, 4 plus 2 will give us 6 pi, and we know that it has got the 0 value. So sine, we have used just the property of sine for m not equal to n. We have just got this integral as to be equal to 0. Now we have to show for m equal to n. This is the case 2 of this problem, since we are going to show whether these solutions are orthonormal or not. This becomes a crucial factor now. We have to check for m equal to n as well. We are left with this integral, which is 1 by pi, simply 1 by pi, 1 by pi. Let me take it to be the common factor, and this will be sine of m minus n, sine of m minus n pi divided by m minus n. Simple. And this second term will simply be minus of sine m plus n divided by m plus n pi. This, let me put it clearly in the brackets. So we now see that we will use the similar argument for the m plus n. We know that m and n are integers, and if m is equal to n, it will be simply, if n is 1, we will be simply getting sine of 2 pi, and we know that it's 0, and clearly this second term in here, this second term will be equal to 0, and we are left with the first term only. Now if we see what we have to solve, we have to solve for m equal to n, and m, this expression, if we see, this will be having 0 by 0 form, and we all know that if some expression will be having 0 by 0 form, because m is tending to n, we will be just using the L'Hopital's rule. So we know, let us simply put this m minus, let m minus n be equal to t. So I will simply write it to be equal to t, and I will get the expression. Since this has gone, we are left with only this. I will get sine of t pi by t. Now I know m has to be equal to n, so this limit t has to tend to 0, and this expression will be sine of t pi by t. And now we will use the L'Hopital's rule, and we will simply get it to be 1 by pi limit 1. Okay, you are writing the answer. It should be pi. Fine. Okay, 1 by pi. Yes. Absolutely correct. Good, good going. Sine of t pi. Be lively in the lectures. That's good. Sine of t pi, and it will, since I have used this L'Hopital rule, it will simply be cos of t pi times pi, and this pi and pi will go, and as he rightly said, we'll be left with 1. So if m equal to n, we will be getting this integral to be 1, and that's what we simply wanted to show that it is orthogonal as well as it is normal. It has the magnitude 1. So this orthonormality condition is satisfied. So the solutions, we can write it like this: the solutions of the Schrodinger equation, Schrodinger equation to the infinite potential are orthonormal. So we have seen this problem as well. Now let us see the, I think I will be able to just show one problem more. Let us see another problem which I have put, that this, I will be just simply introducing you to the concept of the commutator. This commutator simply is the, it, what does it signify? I have just written what does it signify. It will tell us whether we can measure two observables at the same time. And as we all know that we have this Heisenberg's uncertainty principle, and we will be seeing its implications over here as well. So if we see that we have this commutator operator for this x and p, we can simply write this x and p when operated on psi will simply, let's first write down this commutator operator itself. It will be simply a comma b, a b minus b a. So if we use this for this position and momentum operator, we will simply get it to be equal to x will be the position operator. Let me put it like in x hat, and this momentum operator will be p hat, and this will be operating over psi x, and we will use this px acting on x and this psi x. This will simply, if we know now we know that for position operator x will be x, and the momentum operator p bar, we know it is given by h bar by iota d by dx. Simple, as taught by the professor in the lecture. So we can put this value of p bar p hat and this x hat, and what we will be getting getting simply x h bar by iota d by dx of psi d by dx of psi, and with the minus expression we will be getting this minus h by iota d by dx of x minus h by iota d by dx of x psi. So we will be, since this is a function of x, let's not get confused. So we will just use the product rule again, and we will get h bar by iota d psi x by dx minus h bar by iota. This will be the minus h bar by iota, and since this is x, we will be getting it to be x d psi by dx. This is simple, the product rule that we have used over here. So simply this term and this term will go, both of these terms will go, and we will be left with this, we will be left with minus h bar by iota psi of x. So simply x of p psi of x has got to be equal to x comma p equal to, if we now see, we know that iota squared is equal to minus 1. We can write it to be iota square by iota, and this will simply be equal to x comma p equal to h bar iota. So this is what we wanted. This is our result, as we have shown that this position and this momentum, we cannot measure them at the same time because we have simply got some value for it. So I had one question in the beginning by uh, Thalapasai, and I will like him to unmute himself and ask that question. Is he present? Let me check. Oh, okay, you can ask, you can unmute yourself.
Yes, sir. My question is simple, sir. Can you please tell more on numerical oriented, sir? If it would be more useful now, sir. You are deriving now, sir, in the same way. If there is any data, like any application or oriented, you need to find out this value, it would be more
Oh,
helpful now, sir.
okay, okay. You want to use numerical values like what
Yes, sir.
energy values I am taking or like that.
Yeah,
Uh,
yes, sir.
since this,
Yes, sir. That's it, sir. My question is answered.
okay, okay. I will definitely go that way. But since this topic was more related to the quantum mechanics,
Yes, sir.
I preferred to show some of the basic things that
Hmm.
you will, if we want to dive deep a bit in this quantum mechanics, you can get a bit insight just by going through these things. I know that it might be a bit hard at this time to get these things because
Hmm.
uh, as time progress in the course, you will see as this course is itself not on the quantum mechanics will just be needed for the basic introduction, and its just implication will be on the effective mass sort of how we get the band diagram, how we are able to get the band structure, as will be taught by the professor in the upcoming lectures. And this quantum mechanics, I just wanted you to get the taste of this, and from the next class onwards, when we will go into the more towards the numerical parts that will be involving like the density of states, carrier sort of things, the FETs like BJTs, MOSFETs, PN diodes, and like those things. And then when we will be moving towards the thin films, I will orient my discussion more towards the numerical sessions. solving the numericals only. Since this in this lecture, I have just tried to give you some concepts about what professor taught. How, like in this example, professor had taught that the solutions of the infinite potential will have a particular form, but the solutions are orthonormal in the infinite potential well. I just wanted you to get the feel of that. That's why I just took the simple problems. And similarly, if I just showed that this velocity thing, how we can get the velocity of these uh, particles. And this first question was simply that if I have some realizable state, and this is the important concept, and you will be having assignment questions also on these things, whether that particular state is physically realizable or not. There are these are the main properties of the wave function that you need to understand. That wave function has to be continuous, like that. It has to be the particle has to be somewhere in the space, sort of things. You have to know these things. And since these are just to give you an idea, brief idea, and uh, just to clear your concepts about the quantum mechanics, since we will not be dealing mostly about the quantum mechanics in the future. This may be just the last lecture or last assignment about that thing what I am talking about today. And in the more upcoming lectures, it will be in more number oriented game.
Yeah, sure, sure. Thank you, sir. Thank you, sir.
I have another question. In question 3, can you explain me the second case last line where you use the L'Hopital rule? Okay, so here you are saying where I use the L'Hopital rule. Since I will be just derivating the above term sine of t pi, it will simply come out to be cos of t pi multiplied by pi, and this the numerator and in denominator we are just having t, and we will be differentiating with respect to the t, and it will simply come out to be 1. That's why we have just written it to be pi times cos of t pi, and we have put the limit t tending to 0, and we know that cos of 0 is 1, and we will be getting it simply to be the pi by pi, and that pi by pi will simply be 1, and we are left with this 1 for m equal to n condition. So the question is, where should I find the ppt? Hmm, I I don't know myself, but most probably it will be with the NPTEL team, and they will be sharing this. They will be sharing this on the portal itself. From what I get it. So, is there any question? So, if there is no question, you people can leave, and we will meet. Okay, I will share the PDF as well as the PPT. No problem here. So if you have no question, you can leave the meet. Uh, Email address that is in the PPT itself. So I request everyone to leave the meeting if they have no question. Thank you, Alpha Sign. So I think there is no question. Let me end this meeting. So thank you for joining the meeting. I'm hopeful that you will be joining the next meeting as well. Thank you very much.